Merci beaucoup. Merci pour l'invitation. I'll speak in English if that's okay, but obviously people should feel free to ask questions in French if they want. So I should mention I'm linked with BrainChip. BrainChip is a company that's making ASIC chips for doing spiking neural networks that bought out the company I set up in 1999, SpikeNet Technology. So I'll mention a little bit about what they're up to later on. But the introduction is actually just saying, I'm saying sort of pretty much the same thing you've heard from Aida and Damien. That the state of the art now is clearly deep learning neural networks. Typically, they use floating point numbers for the neuronal activation levels and connection strengths. Although Damien gave us illustrated, we can do it with binary weights for the inference stage, maybe. But the fact is that real neurons use spikes. Now, is that a problem? Well, for many people, they don't care about this because they just say that the floating point numbers are just representing the firing rates of neurons. So we don't really have to worry about spikes. We just, we can just convert firing rate into a floating point number and it's the same thing. But that, I think, is fundamentally wrong. Doing stuff with floating point maths is a power disaster. Rate coding is a disaster. Backprop learning is a disaster, and all these things have to be changed, in my opinion. And I think this is relevant for embedded systems, because if you want systems that can actually work under reasonable conditions, I think we have to switch to spiking neural networks, and I'll try and convince you of that. So here's the killer argument, if you like, why using spikes. We know we have about 86 billion neurons in the brain. On average, they might have about 7,000 connections. Let's imagine you wanted to do a huge neural network system and recalculate the state of every neuron every millisecond. You would need 600 petaflops. And the most powerful computer on the planet currently is the supercomputer, the Fugaku supercomputer at the RIKEN. It does 500 petaflops. And it's using nearly 30 megawatts of power. Okay. Now the brain, as has been pointed out by Aida and Damien, is using 20 watts. There's something seriously wrong here. And for me, I mean, we've heard some other ideas. Aida was talking about using oscillators. Damien was talking about in-memory computing. My slant on this is that another key difference is that neurons use spikes, which can be extremely sparse. You only have to send information when the neuron spikes and not all the time. I should point out actually that the deep neural networks and embedded computers are making progress. So for instance, NVIDIA, you might know their Jetson family of processors, which can be used for embedded processing. And for instance, you can get nearly 2,000 frames a second on some of these standard neural network benchmarking problems. So the biggest chip that they produce, the AGX Xavier chip, will do 11 teraflops and even more if you cut down the precision down to 8-bit integer. So relative to the supercomputer, you could actually do the brain with 50,000 Jetsons if you had enough money to spend. That would give you the power, but it would still be using 500 kilowatts. So it's better than a supercomputer, but it's still not particularly good. It's 25,000 times less efficient than a human brain. So the alternative strategy that I'm going to push is that we should rethink neural coding from the starting point. Classical neural networks essentially all assume that what neurons do, I've got 16 neurons here, they're sending floating point numbers, I've got floating point numbers for the weights, I multiply them all together and get a final activation value, then I take that sum and I put it through some output function, could be sigmoid or a rectified linear function. But all of these are very expensive computations, and that's why the current AI systems are really very, very power hungry. Now, you can get some savings by reducing precision. And we saw that a bit with what Damien was talking about, the binarized samples. And NVIDIA's latest chips have a whole range of different things. You can get right down from floating point down to integer stuff if you want, into binary. They also have a sparsification thing where you can get rid of 50% of the weight. So, you can get the whole thing going around 256 times faster than if you're using floating point numbers. This is nowhere near enough to get us anywhere like human brain efficiency. Another so I'm going to mention BrainChip here. They got a chip coming out soon, the Akida chip, which also uses reduced precision. It will do 4-bit, 2-bit, or 1-bit weights. You can have a neuron with 160,000 binary inputs, for instance. I won't go into the details, but basically this has got sort of 80 neural processing engines which are running together, and you can get sort of 1.5 tera operations per second, which is not bad for a chip that uses a fraction of a watt and only costs about $10 to produce. So actually, this is an Akida chip on a development board here. That's Peter van der Meijde, who was the founder of who is the CEO, currently CEO of BrainChip. And they were promising they're getting the production quantities, beginning of 2021. It's going to be in a couple of months, hopefully. So I'm really looking forward to see what these chips can actually do. But even if you reduce the precision down to 4-bit or whatever, it's still basically you're doing the same sort of thing. You'll be using 4-bit activation levels and 4-bit weights, but you still do the same thing. It's just less precise. You get less accuracy. It reduces the power consumption by some degree, but it's not really going to change the game. Moving to the spikes is much more significant. The reason is that the mainstream view, which dominates, in my opinion, 99.9% of all research, is that spikes are using rate coding. This is what everybody assumes. And there are several methods that you could use when you're using spikes to code an analog value as a rate code. And I will mention a few of them. There's standard rate coding, where you count the number of spikes in a fixed time, like 10 milliseconds. You can measure the interval between two spikes. That gives you an instantaneous estimate of the firing rate. You can use population rate coding, where you count the spikes across a population of neurons in a fixed time. In a millisecond, you can measure a firing rate if you've got 1,000 neurons in parallel. You can use label line coding, where individual neurons spike for a specific value. And if you believe the neurophysiology, you're supposed to be using Poisson rate coding, according to which neurons have an internal Poisson rate generator, which is totally insane. But that's what a lot of people apparently think. Now, I want to just kind of convince you, none of these are any good. These are really, really bad ideas, and we should be doing something different. Let me just run through the idea. So classic rate-based coding. This is the idea. We've got 16 neurons here with 16 different firing rates and 16 different weights here. And here we're coding effectively 4-bit activation levels and 4-bit weights and everything. So you can get that to work, okay? The trouble is there's no control over the distribution of input values. There's no control of the distribution of weight. And here's the killer thing. Look at the fact that the first spike latency is already telling you what the answer is. There's all these other spikes here basically are a waste of time, because the 136 spikes here are telling you nothing more than you got from the ordering of the first spikes. And we'll get back to that in a moment. Another idea is using the interspike interval, where we measure the interval between two spikes. Now, again, this could be done, but there's no information when there's only one spike. And actually, it's incredibly difficult to decode. Some people think that you could have synapses which are sensitive to paired pulse potentiation, for instance. So they'd only get a big signal if you get two spikes within 4 milliseconds or something. But this is incredibly difficult to do as a strategy. I wouldn't recommend it to anybody. Population rate coding, that's the idea that, well, we don't have one neuron, we have 16 neurons in parallel, and we count the number of spikes across the different channels. So here we've got We got 16 channels for input A and 16 for P, and we can count the spikes. But this is ludicrously expensive. We're using 16 times as many lines and 16 times as many synapses. And also, when do you stop? I mean, I could stop listening to spikes at any point. I don't know when I should finish counting the spikes across neurons. I mean, so none of this makes any sense. Labeled line coding. I've heard this one. This is another wacky idea which makes no sense. This is the idea that you have neurons that only respond at a particular value. You know, they have a, you know, only if it's within the input is between one value and another. Doesn't happen in the real world. And again, it's very expensive because we're having to use lots of channels for every to code every value. And then finally, Poisson rate coding. This is the idea that, you know, we've got these neurons are generating a random process. Well, Jacques Gautret and I did some, well, Jacques did the maths, basically you can prove that this is a disaster. I mean, if you wanted to send any information with a Poisson rate code, it would be hopelessly inefficient. You know, the retina could not get enough information to the brain to recognize an image at all. It's just no way it can happen. And in addition, actually getting a neuron to generate a Poisson rate code is, I don't know how to do it anyway. So for the last 30 years, I've been pushing the idea of temporal coding. That's the idea that we got neurons here with an input profile of activation, and those neurons fire spikes in a wave where the most strongly activated cells fire first, and you can get information in the order of firing. It's a natural consequence of the fact that sensory receptors, for instance, in the retina, are a bit like a capacitor with a threshold. With a weak stimulus, the time taken to reach the threshold is longer than with a medium stimulus or a strong stimulus. So what this produces is an intensity latency function. As you increase the intensity, the latency drops. It's in other words, sensory neurons are intensity delay converters. They're not well, in a sense, they will be an intensity to rate coder if you let the system keep firing. But you didn't need that information. Now, you know, and you could. This is that figure I just showed, where you can see, you know, what I'm talking about. This is the same thing as produce this function here. It's just, you know, charging up a capacitor. Now, the amazing thing is that the very first person to record neurons in the visual system, Lord Adrian in Cambridge in the 1920s, he got the Nobel Prize for this. He was recording from the EEL visual system. He was recording and counting the number of spikes that were being generated in a few fibers in the optic nerve. This paper, published in 1926, did an experiment where he was measuring the firing rate to a point of light which had two intensities, high intensity, low intensity. And you can see that when you have the high intensity stimulus, the firing rate, this is not one fiber, it's a bunch of fibers, but anyway, it's a similar sort of thing. You can see it's a higher firing rate, and it's a higher maintained firing rate as well. So you know, the stimulus comes on for 3 seconds, and it's still firing a lot higher there. No, rate coding, right? But look, the latency of the onset is very different. It's like twice as long with the low intensity stimulus. This was in the very first paper ever published in 1926 or 27, and it showed that the retina is an intensity to delay converter. And that basic physiological fact was ignored literally for several decades. And I think we only really started thinking about this idea in the late 80s, right? And it was actually proved for the retina, you know, in a paper in Science in 2001, I think, or something. Now, if you buy the idea that you can get information by looking at I mean, here we've got my 16 cells and they're firing spikes at different latencies. Back in the late 90s with Jacques Gautret, my thesis student, we showed that actually you can decode this with a fairly simple circuit where you have neurons with different weights, synapses with different weights, and a little circuit which does a sort of shunting inhibition thing, which as spikes come in, this desensitizes the neuron. And I won't go into all the details, but we have a little model whereby every spike as it comes in gets less and less effective. The first spike to come in is 100%. The second one, 85%. Third one, 85 squared percent, if you like. And this produces an activation function as spikes come in, which can only be maximal if the inputs fire in the order of the weights. So if you fire in that order, you get to this value. If you fire in the reverse order, you get to this other value. If you fire any of the 21 trillion possible orders with 16 inputs, you get something in between with an average which is halfway between the two, and 1% of the time you get over this. This is an incredibly selective mechanism. We thought this was really interesting, but it does require accurate weight control, which is not trivial. And we never managed to come up with a nice physiologically plausible learning rule that would actually set the weights to those values. So what happens if you don't adjust the weights accurately, but you just use binary weights, as Damien was talking about earlier on? Well, you can do a thing which we call N of M coding. And the trick is we have a little circuit here. We've got these neurons firing spikes, but we have a little circuit, the relay cells, which will transmit the site. This is exactly what happens in the geniculate, by the way. And as soon as a certain number of the inputs are fired, the inhibition clamps all the other neurons and prevents them from firing. So we have 4 spikes get through of the 16. So when you have 16 inputs and 4 spikes, and if you have a neuron with 4 weights, the probability of hitting your 4 weights, binary weights, by chance with a random input is like 0.05%. Now, that's simply because there are 1,820 different ways of choosing 4 out of 16. And that number goes up enormously as you increase the N, the number of channels. So if you've got 2,048 inputs, the probability of getting 4 hits is like 1 in a trillion. Now, we actually developed that idea in SpikeNet Technologies Recognition Engine, which we developed between 2001 and 4, and we never published it. And I'll tell you the reason why we never published it is because it was the company's secret sauce that we didn't want to tell anybody about. But actually, we knew that this worked. Interestingly, Steve Ferber, the guy behind Spinnaker, actually came up with the same thing. He called it N of M coding in a paper in 2004. This was literally, this was great minds think alike, because we'd actually come up with, we realized just how powerful binary coding is when you control the number of inputs that fire. So let's take an N of M coding circuit. So as I say, the first thing to do is to convert those intensity values into a wave of spikes with the most active inputs firing first. It generates a sequence of spikes. In this case, this is the sequence, right? Then we have it's actually a winner-take-all circuit, a K winner-take-all circuit where you can fix K. Here I've fixed it at 4, so N spikes get through, K is 4. So only the first N spikes get through. Now we have neurons that have a fixed number of binary weights. Here I've set the number at 4, and you can just calculate when N is 16, M is 4. Oh, sorry, I've got this wrong way around. It's sorry, M is 16, N is 4, and each neuron has 4 weights. So you can calculate what you would get as a number of matches by chance. Most of the time, this is the hypergeometric distribution. Most of the time, it's going to be 1, as you can see here. Sometimes it will be 0. Sometimes it will be 2. Very rarely you'd get 4 by chance. Now, if you what you'd like is a neuron that is tuned to pick up this. So this neuron here will fire if B, C, J, and K fire first in any order, and the chance of that happening by chance is less than 1%, as I say. Now, how can we train the neuron to do that? Well, this is where we came up with an idea called JAST. JAST because it was Jake Martin, Amir Yousefzadeh, me, and Tim Maskilier. And basically, the idea is the following. A neuron has random connections to start off with, and it has binary connections. It has 2 thresholds. One is the threshold for spiking, which could be 4, but then it also has a threshold for learning, such that if you get 2 hits, which is actually not very likely, you activate a learning mechanism which moves one of the unused weights to a place where an input was active, like this, for instance. So now if we have the same input again, it will produce 3 hits rather than 2. And we can move the learning threshold up to 3 now, such that we'll do the same thing. So again, we will move another unused weight to match the input that was present. And bingo, we now have a neuron which in 2 learning trials will detect any sequence with B, C, J, and K in the first 4. And you can have lots of neurons. Each one of them has learned different patterns. So this second neuron would like O, M, D, and H in the beginning. This one likes P, L, C, and G. This one likes K, M, O, and A. As I say, the precise ordering doesn't count. What's important is that a particular set of inputs fires get through first. Now, the interesting thing, you can calculate how selective these mechanisms here. We've been talking here about this case where M is 16, N spikes and M 4 weights, and that's the 0.05% chance of getting 4 hits by chance. But as you increase the number of input channels, the probability of getting 4 hits drops enormously. And you can do the same thing by fixing the percentage of inputs. Here we've got 100 inputs, 10 spikes, 10 weights. The probability of even getting 7 hits by chance is tiny. And the probability of getting 10 hits by chance is astronomically low. So you can make very selective systems like this. Now, when we developed JAST, we tried this not with 16 inputs and 16 outputs. We had 1,024 inputs and 1,024 outputs, and we were feeding random spikes into the system. And you can see here all of these neurons, which basically have a fixed number of weights. I think it was 16 in this case. They don't do anything. But if we choose a random spike here, this one with a star, and then take 1 in every 2 spikes and make a motif that's going to repeat. Well, the first time that happens, nothing happens in the output. But on the second time, we got the same pattern of spikes, but actually where half the spikes are actually noise. We've got 2 neurons. On the second trial, we've got 2 neurons that are saying, oh, that's interesting. That reminds me of something I saw earlier. And by the time you've got 6 repetitions, you've got a whole packet of these neurons firing. I mean, you can learn lots of patterns simultaneously. And we had this running on an FPGA. This is the spikes coming into the gray spikes and neurons which are not in the pattern. The blue and red ones are ones which are in the pattern. This is just noise. And then we start repeating the patterns. You can see the output neurons learning here. We go back to noise, the neurons stop, bring the patterns back in again, and they're firing again. And Amir did this on a Spartan 6 FPGA. And this is actually 13 milliseconds. It does the whole thing, learning with 1,000 inputs. It's processed 70,000 spikes, and it's doing on-chip learning in real time. Okay, so we thought it was rather. This is the Spartan 6, and you're sending spikes in here, and the spikes are coming out here, and it's basically, it works, right? And so we patented this. It's still pending, unfortunately, but anyway, BrainChip have licensed the hardware license back in 2017. So I'm waiting for Akida to come out because it's supposed to have our learning rule on it, and I trust it's going to do a lot better than a Spartan 6, but I don't know yet. They're planning to bring out USB compute sticks and also a Raspberry Pi development board anytime soon, like in the next couple of months. So if you're talking about embedded systems, maybe this chip, which costs $10 to build, could be very interesting. So stay tuned for that. Right, so the bottom line is, well, 99% at least of neural network research uses floating point maths. But real neurons don't send floating point numbers, they send spikes. And most people think of that as a rate-based code. And there are lots of ways you could do that. But I hope to have convinced you that all of those are rubbish. Don't do rate coding is the bottom line. Use temporal coding. You could use rank order coding, which is what we did back in the late 90s with Jacques Gautret. But the trouble is you need graded synapses, and even if Damien's going to offer me a thing where you can adjust the weights on your memristors, it's actually nice not to have to do that. and they're difficult to train. But the NFM coding thing, the idea that you limit the number of neurons that are allowed to send spikes to the next layer is very promising, because you can use binary synapse. You've got this JAST learning rule, which can learn in real time on a chip, and it's already been done on an FPGA, Spartan 6, and hopefully in the next couple of months, you're going to be able to see an Akida chip doing the same thing for $10. So the bottom line is that, I think spike-based coding could indeed be a key to developing intelligent, low power embedded devices. And with that, I will open the few minutes left for questions, hopefully.
Thank you, Simon.
So how do we do questions here?
Maybe there are some questions in the room already. So
there are none in the Q&A session yet. So go ahead.
So I have a first question. So thank you for your presentation. On which task did you already try to train your algorithms? What task are you solving with this algorithm?
Okay, well, for the moment, we've been using a fairly sort of generic problem. Finding, we have spikes coming in that can be could effectively be generated by anything like a dynamic vision sensor, retinas, or auditory pathways, and sending spikes. And the idea is that if the spikes are just random, none of the neurons will learn anything useful. As soon as anything repeats in that stuff, we get neurons becoming selective, and these neurons are cheap to implement. So I showed with the Spartan 6, we had actually up to 4,000 neurons on chip learning in real time. I hope that the Akida chip will be able to offer a lot more than that. So we haven't really been pushing what you can use this for yet, I have to be honest. I've been waiting for the stuff to come through, but you could actually use it for processing all sorts of things. I actually got a student thinking about using it for text processing, so you could have ASCII characters coming in, or you could have some people remember Olivier Bichelet's thing on the dynamic vision sensor, Toby Delbrooke's chip that was had cars going by on the freeway. I really ought to try JAST out on that. I would imagine it would do very well, but I have to confess we haven't actually really been benchmarking it.
Okay, thank you. So is there a question? Yes.
So thank you for your presentation. Yeah, and like most AI research nowadays are using like CNNs or neural networks that actually have a kind of memory, of a time memory on their architecture. How this memory can be implemented using this spiking and JASP training?
Well, in a sense, we have the basic JAST thing. We actually process packets of spikes, but we're currently working. A packet would be, you take 100 spikes or something coming from your input, and you process that as a packet. In that case, it doesn't have any memory, but actually, it's not complicated to give neurons a sort of memory so that they can, when you increment their activation, it stays on for an arbitrary period of time. And actually, we're doing simulation stuff with some people at the IRIT for doing this, where you can actually have a neuron remembering, for instance, that it's seen a word for, if you're reading text, for instance, it would work a bit like a natural language processing system that would remember the fact that you've just seen a particular phrase. So it might be able to do text prediction and maybe do the sort of GPT-3 type thing, but a lot cheaper. Because if you're only using spikes, and the spiking can be extremely sparse, and this is something maybe I should stress. that Damien was talking about the binarized synapses, but if you're sending -1 and 1, you haven't actually economized sending values. You're having to send both values all the time anyway. Spiking neurons, when they don't fire spikes, you don't do anything at all. And in fact, I used to, when Arnaud Delorme produced our first event-driven spiking neural simulator in 1998, I joked that we could do the entire human brain in real time using this simulator, as long as none of the neurons fire the spike. That's the point. So unlike conventional neural networks, where you essentially take every neuron in the system and calculate its activation level on every time step based on every input, that's what kills you. The brain only does computing when a neuron spikes, and if you can keep the sparsity down to a very low level, so very few neurons spike, then you can have arbitrarily low power consumption. Sorry, I deviated a bit there.
Thank you very much, Simon. Let's thank again, Simon.
My pleasure. So I'll stop sharing. And
so unfortunately, time is flying. So we